Oh my god, Tim, there's a cockroach on your shoulder!
Where? Die! Psst, psst, psst. Yes, die, ouch!
Okay, yes. Finally, it's dead. Also, I'm very happy to get a chance to hit Tim. So, Tim, do you actually know that an insecticide, right, contains organic compounds with halogens inside?
Organic compounds with halogens? What's that? Can you eat?
Of course!
Mr. Leong, can you tell me exactly what are halogenoalkanes?
So as the name suggests, there is a halogen and there's an alkane to it. So the halogen is obviously talking about my group 17 elements, but they are going to be bonded to an alkane. So more specifically, they're going to be bonded to a carbon, which is going to be saturated over here. So Mr. Tim, can you share with me a little bit more about the classifications of a halogenoalkane there?
Hey, sure thing. Now, guys, just like how Mr. Leong just boxed up the carbon there, we're going to do the exact same thing. Box up the carbon that is holding that halogen there. And Mr. Leong, can you tell me how many R groups we see attached to that carbon?
So we're looking at directly attached to the boxed up carbon. There's only just one.
Okay. Now, so if it's one R group attached to that carbon, we call it primary. If there are two, secondary. And if there are three, tertiary. That's it. Okay. Now, Mr. Leong, how exactly do we prepare halogenoalkanes? Do they just fall from the sky?
Tim, that's a very wishful thinking, but we prepare it in the lab. So shall we take a look at some of the reactions that we can use to prepare these halogenoalkanes?
Let's go.
Now the first of which is going to be using a alkane to give me the halogenoalkane. We're going to introduce a chlorine into the system, and what's going to happen is that we're going to replace the H with the chlorine. Now this reaction requires you to use UV light. So Mr. Tim, can you share with me which reactions uses UV light?
Whoa, UV light. This reminds me of alkanes, right? That free radical substitution reaction.
Okay. Yeah, that's right. So as the name suggests, substitution means that the H is going to get replaced with the chlorine, and as a result, we're going to produce a HX as a side product. Now this reaction, unfortunately, Mr. Tim, do you usually use this in your lab last time?
We don't.
Why not?
Because you get a variety of products and you don't want that, right? You just want your RX.
So this is a very sucky reaction, in fact. So nobody really uses this reaction. So since there is such a sucky reaction, shall we take a look at a different reaction?
Sure.
We're going to use an alkene instead now.
Okay.
Yes, a CC double bond. So Mr. Tim, can you just share with me what kind of reactions do they undergo?
Sure thing. Now, alkenes, we know that the double bond is electron rich, right? There are pi electrons in there. So alkenes, remember, it is nucleophilic. And if it is nucleophilic, it's going to react with electrophiles. Now, is it addition or is it substitution? Now, alkenes are unsaturated, so it's definitely going to be addition, right? So electrophilic, and electrophile is going to add in addition.
That's right.
Good.
So how do we introduce a halogen inside? Of course, your reactants must contain a halogen. So if you want to introduce one halogen, we're going to use HX over here, right? And that is going to introduce one X inside. But if you decide to be a bit funky, you want to introduce two X's, then we have to use a slightly different reagent. What would that be, Mr. Tim?
Then we're going to use, so if you want two halogens to go in, we're going to use X2. But in this reaction, we have to be careful because you need to make sure it is done in the dark. If you do it in the presence of UV light, now remember guys, your product, it is still an alkene. So if there is UV light present, Mr. Leong, what's going to happen to this product?
You're going to get multi-substitution.
Exactly. It's going to further react with X2 via FRS. Okay?
So these are two very good reactions to produce my halogenoalkane, depending on whether we want to introduce one or two halogen.
Exactly. Yep.
Okay. The last reaction might be a little bit new to you guys, but I'll just briefly give you an idea about it. We're going to start off by using an alcohol to turn it into a halogenoalkane. So in this case, I'm going to use my favorite reagent and condition. There are a couple of them, but my favorite is actually PCl5 in the solid state, done at room temperature. So since I'm using PCl5, I'm going to replace the OH with the Cl. The type of reaction is going to be known as a nucleophilic substitution reaction. Now, since that I've prepared this halogenoalkane now, right, I can have my own baygon, right, Tim?
Yes, you can. Actually, I want to prepare my own bay Tim. Tim is a bay, get it?
Very funny, Tim. Okay, now that I have my own baygon or bay Tim, I'd like to take a look at what kind of reactions can they undergo. Bay Tim, can you help me to do that?
Of course. Now, let's go. So, Mr. Leong, with every organic chapter, right, you always have to think, our reactants nucleophiles or electrophiles, right? Now, wait for it.
Wow, Tim, you're very dramatic, okay? Let me just go straight into the chemistry behind it. So we understand that a halogen, they are all from group 17, so they must be very electronegative atoms. So Mr. Tim, remind me again, what's an electronegative atom?
Well, if I'm electronegative, then I really like to pull electrons from you, right? And this makes carbon electron deficient.
That's right. So this carbon would be electron poor, and that is why in general we can say that halogenoalkanes, they are going to be electrophilic. Now, electrophilic or electrophiles, right, they don't really undergo electrophilic reactions. In fact, they get attacked by a nucleophile, so therefore they undergo a nucleophilic reaction. Now, next question for you, Mr. Tim. Do you think your halogenoalkanes will rather undergo substitution or addition?
Well, for us to undergo addition, our reactor needs to be unsaturated, right? But it's a halogenoalkane. And so therefore, it is saturated. It cannot be addition. It needs to be substitution. So nucleophilic substitution.
Right. So now we can take a look at an example to really illustrate why does it undergo nucleophilic substitution. So just to remind you again, we say that a halogen is very electronegative. It acquires a delta minus charge, causing the carbon to be electron deficient. Now the nucleophile would like to come in to attack this electron deficient carbon, causing the CX bond to break simultaneously. So what's going to happen is that you notice that the X over here is going to get replaced with a nucleophile, and as a result, we're going to give X minus as a side product.
Okay.
So actually the mechanism is not so simple. In class, I'm going to show you two more detailed mechanisms. 恭喜发财!